Today's topic is time varying magnetic field. Lorentz force acting on a charged particle due to magnetic field is EV cross B. If charged particle have charge E, velocity V, then force due to magnetic field B vector is given as EV cross B. And it is direction of this force will be perpendicular to both V vector and B vector. So it is always perpendicular to velocity v, and the path of charged particle is circular. So magnetic field itself cannot impart energy to a charged particle. Now if the magnetic field B varies with time, there will be electric field E associated with it, and this associated electric field is given by this Maxwell equation. Maxwell equation is del cross E equal to minus delta B upon delta T. This equation shows that time varying magnetic field will produce electric field. Electric field E is produced because magnetic field B varies with time t, and del cross E is equal to negative of this time derivative of B. We write delta B upon delta T as B dot, then we can write this equation as del cross E equal to minus B dot. We write this equation as equation 1. It is Maxwell equation, del cross E equal to minus B dot. Now this can accelerate the particle. If we have constant magnetic field, charged particle move in circular orbit in a plane perpendicular to the direction of magnetic field. So if magnetic field is constant, it will not impart any energy to the charged particle. But this magnetic field B, if it varies with time t, then it produces an electric field E, and now this can accelerate the particles. Let V perpendicular equal to dl upon dt be the transverse velocity, neglecting the parallel component V perpendicular vector. Velocity of charged particle is V vector. We consider its two components. One is V perpendicular and other is V parallel. V parallel is parallel to B vector, and V perpendicular is the perpendicular to B vector. This V perpendicular, it is the transverse velocity. We write it as dl upon dt. dl is a small displacement in a small time interval dt. Displacement upon time. So V perpendicular vector is written as dl upon dt. Here L vector is the element of path along a particle trajectory. Equation of motion of charged particle is written as m dv upon dt equal to q into E vector plus V vector cross B vector. We have time varying magnetic field B vector, and this time varying magnetic field B vector produces an electric field E vector given by this equation. So we have force due to electric field E and force due to magnetic field B. In left hand side we have mass into acceleration, m into dv upon dt, and it is the force, and this force is equal to q into E vector plus V cross B. QE is the force due to E, electric field, and QV cross B is the force due to B, due to magnetic field B. Taking the scalar product of above equation with V perpendicular vector we have. If we take a scalar product, that is dot product, of this equation, which is equation 2, on both the sides we take dot product of left hand side and right hand side of this equation 2 with v perpendicular vector. It means in left hand side we have m dv upon dt dot v perpendicular, m dv vector upon dt dot v perpendicular vector. We take the dot product of this equation with v perpendicular vector. So left hand side becomes m dv vector upon dt dot v perpendicular, and this becomes d upon dt half m v perpendicular square. If we differentiate half mv perpendicular square and v perpendicular square, we write v perpendicular vector dot v perpendicular vector. Then this differentiation will give the term m dv upon dt. d upon dt v perpendicular square is d upon dt v perpendicular vector dot v perpendicular vector, and it will give, using first function differentiation of second plus second differentiation of first, it will give v perpendicular dot dv perpendicular upon dt plus dv perpendicular upon dt dot v perpendicular, which is equal to 2 times dv perpendicular vector upon dt dot v perpendicular. So this is the left hand side of this equation. We ignore here the parallel component of velocity, v parallel. And in right hand side, if we take dot product with v perpendicular vector, in first term we get qe vector dot v perpendicular vector, and in the second term this dot product will become 0, because it will be dot product of v vector cross b vector and v perpendicular vector, and direction of v cross b is perpendicular to v, and if we then take dot product with v perpendicular, it will become 0. So only this term in right hand side remains, that is qe vector dot v perpendicular vector, and we put the value of v perpendicular vector as dl vector upon dt. Now this half mv perpendicular square is the kinetic energy, half mv square, and d upon dt is its differentiation. The change in one gyration is obtained by integrating over one period. If we integrate this equation for one time period means time for tracing a complete circle. A charged particle in magnetic field moves in circular orbit, that is known as Larmor orbit, and if time period of that circular path is capital T, that will be equal to 2 pi upon omega c. Omega c is cyclotron frequency for that circular path. So if we integrate for one period, left hand side will give delta half mv perpendicular square. If we integrate for one time period, then integration of the term of left hand side will give change in the value of half mv perpendicular square, and we write it as delta half mv perpendicular square. And in right hand side we are integrating with respect to time t for one time period. So limits of integrations are 0 to capital T. Capital T is time period, and that is equal to 2 pi upon omega c. T equal to 2 pi upon omega, and omega is omega c, cyclotron frequency. If the field changes slowly, if magnetic field changes very slowly, we can replace the time integral by a line integral over the unperturbed orbit. In right hand side we can convert this time integral into line integral. We can assume it as dt is cancel out and remaining integral is for dl, and it is line integral. So we write a symbol of circle inside the integration which represent that this integral is line integral for that circular orbit, for Larmor orbit. And now this line integral can be converted into surface integral by using Stokes theorem. We can change this dl vector into ds vector. Line integral, to convert it into surface integral, we write ds vector in place of dl vector. Then we have to write del cross E in place of E. So in place of E we write del cross E, that is curl E. Then we write in place of dl vector we write ds vector. In this way this line integral can be converted into surface integral using Stokes theorem. Now this surface integral is for surface area S, and S is the surface area enclosed by this closed curve. Closed curve is closed circle. It is the path of charge particle, circular path of charge particle. This circular path of charge particle, if it encloses area S, then the integral for right hand side is for surface area S, and we can write this as equal to minus q integral b dot ds. Here we use the relation del cross E equal to minus b dot, which is Maxwell's equation, equation 1. Del cross E is equal to minus b dot. So this becomes minus q integral b dot ds. Here S is the surface enclosed by the Larmor orbit. Since plasma is diamagnetic, we have b vector dot ds vector less than 0 for ions, that are positively charged particles. This is the flux b vector dot ds vector, it is negative. And this b vector dot ds vector is greater than 0 for electrons, which are negatively charged particles. Then equation 4 becomes, this is equation 4, it becomes delta half mv perpendicular square equal to plus minus, this right hand side becomes plus minus q b dot pi rl square. Plus is sign for positively charged particle and minus is sign for negatively charged particles. Q is here and b dot is here. B dot ds vector then after integration will give B dot into pi RL square. Pi RL square is the area enclosed by closed Larmor orbit. RL is the radius of this circular orbit. It is known as Larmor radius. So this integral will become B dot into pi RL square. Pi RL square is the total area. And now we write RL square equal to V perpendicular square upon omega c square. That is RL, Larmor radius, is equal to V perpendicular upon omega c. Here we use the relation V equal to omega R. Then R is equal to V upon omega. V is V perpendicular and omega is omega c. R is RL. Now this right hand side becomes as plus minus q b dot pi V perpendicular square upon omega c square. Now in this term, in denominator we have omega c square. We write it as omega c into omega c, and for second omega c we write its value, which is plus minus qb upon m. Omega c is cyclotron frequency for circular path, and it is equal to plus minus qb upon m. Now this term can be written as half mb perpendicular square upon b into 2 pi b dot upon omega c. Q is cancelled out. We write this term in this form: half m v perpendicular square upon b into 2 pi b dot upon omega c. Half is not present in this term, so we multiply by 2 and divided by 2 and get this half term. The quantity 2 pi b dot upon omega c, it is here in this term 2 pi b dot upon omega c. This quantity is just the change in magnetic field during one period of gyration. Look at this quantity 2 pi upon omega c into b dot. Here 2 pi upon omega is time period. 2 pi upon omega c is time period for Larmor orbit, for circular path. And b dot is delta b upon delta t. B dot is change in b per unit time, and if we multiply by this 2 pi upon omega c, that is time period, then it is change in b in one time period, that is in one complete circular orbit. We write this change in b as delta b. So 2 pi b dot upon omega c will give delta b. It is the change in b in one time period during one period of gyration. If mu is the magnetic moment of the gyrating particle, then we can write half mv perpendicular square equal to mu b. If a charged particle having magnetic moment mu and it is placed in magnetic field b, then its potential energy is given by minus mu vector dot b vector. In left hand side it is the kinetic energy, half mv perpendicular square, and in right hand side it is the magnitude of that potential energy, mu b. So half mv perpendicular square is equal to mu b if mu is the magnetic moment and b is the magnetic field. If we write half mv perpendicular square equal to mu b in this equation, then put half mv perpendicular square equal to mu b. Then this b is cancelled out by b in denominator and mu only remains. And the next term is 2 pi b dot upon omega c, which is delta b. So right hand side will become mu delta b and left hand side is delta mu b, because half mv perpendicular square is mu b. Half mv perpendicular square is mu b. So left hand side will become delta mu b and right hand side will become mu delta b. Now this left hand side will become mu delta b plus b delta mu. First function differentiation of second plus second differentiation of first. Treat delta as differentiation. And now this is equal to mu delta b. Mu delta b is on both sides, so it cancels out. And we have b delta mu equal to 0. Since b is not equal to 0, delta mu is equal to 0. Delta mu is change in magnetic moment of the charged particle. So the magnetic moment is invariant, that is constant, in slowly varying magnetic fields. As the B field varies in strength, the Larmor orbits expand and contract, and the particles lose and gain transverse energy. Equation 6 describes this exchange of energy between particles and the field. Now we see that the magnetic flux through a Larmor orbit is constant. The magnetic flux through a Larmor orbit is phi is equal to b dot s. S is the area of Larmor orbit, that is pi RL square, pi r square. R is RL, Larmor radius, and Larmor radius RL is equal to V perpendicular upon omega c, using V equal to omega r. V is V perpendicular, omega is omega c, cyclotron frequency. R is RL, Larmor radius, radius of Larmor orbit, that circular orbit. Now we put the value of omega c square. Omega c square is q square b square upon m square. Value of cyclotron frequency omega c is plus minus qb upon m. Put this value here. Now this is become equal to half mv perpendicular square upon b into 2 pi m upon q square. And half mv perpendicular square is equal to mu b from this relation. So if we put half mv perpendicular square equal to mu b, then this term will become equal to mu into 2 pi m upon q square. And mu, magnetic moment, is constant here. From this relation, delta mu equal to 0, that is change in mu is 0, so mu is constant. So magnetic moment mu is constant, and other terms having m and q are also constant. So we see that this flux phi is constant. As magnetic moment mu is constant, flux phi is also constant. This property is used in a method of plasma heating known as adiabatic compression.